floor is yours. Thank you.
Thank you so much, guys, for being here. Thank you so much to the staff team for making this possible. So scaling Ethereum, the power of UTXO. We are going to understand why we need to scale Ethereum. We are going to understand what's an UTXO. But this is Vitalik 6 months ago. This is 2023, later 2 days in Istanbul. Bulletproof Vitalik did an amazing talk that day. 2 key takeaways. The first one is Vitalik talking about plasma, which is quite crazy. And Vitalik talking about UTXO, which is today's topic. So we are going to talk about the state bloat and decentralization issues. We are going to talk about race condition and execution issues. We are going to talk about UTXO indeed. We are going to have a quick view of the history of UTXO by the work of Hal Finney. We are going to talk about the state minimized design. We are going to talk about predicates. And we are take a very quick look to some projects using UTXOs right now. So, state bloat and decentralization. State bloat is the situation where increasing state in the blockchain leads to increasing hardware requirements for the validator nodes. Basically, increasing hardware requirements threatens decentralizations because more hardware mean more money, and not everyone can run a node, so the network gets centralized. This is a chart portraying how Ethereum state is growing non-stop since the beginning, but not every kind of a state is the same kind of a state. So we can understand like basically 3 kinds of state growth issues. The first one is state growth, which is new accounts, new bytecode, new storage. We can see history growth, which is new blocks and transactions, and we can talk about state access, which is the issue of reading and writing operations for building and validating blocks. Today, we are just focusing on state growth, which is new contracts, bytecode, and contracts. Right now, the Ethereum state is up to 245 gigabytes on a red node, which is a lot. Mainly we have accounts, which is 14%. Then we have bytecode, which is 4%. And then we have contract storage, which is 81%. A lot of memory spent there. Seems like it's fine, but it's not. It's threatening the whole Ethereum ecosystem. And as you can see, somewhere around 48% of current Ethereum storage is basically ERC20 and ERC21 transactions. So it's like we are spending a lot of resources just to tracking assets. So summary, state bloat is bad. Then we have another issue, which is the race condition. Some of the computer nerds out there might understand this concept, which is, this is like a block header for an Ethereum block. An important step might be the state root, which is the root of the merkle tree of the state of the block. And basically, Ethereum storage looks like this. It's a dictionary where you have account names and ETH balances. And for the case of contracts, you have like the ETH balance, and you have another storage root representing the contract storage, which for ERC20 might be like just accounts and balances of that specific token. So the question might be, why is not parallel? Like, what's the issue behind the account model to make the parallelization impossible? Well, because of race condition. Race condition is a situation where 2 processes or threads are trying to access and update the same slot of data. Looks like this, but basically. And Ethereum did some work trying to solve this issue. This is a screenshot from the EIP's GitHub. Basically, this is Vitalik proposing somehow some kind of access control list for execution. So basically, the node can know beforehand which storage slot are being updated. There's a lot of interesting information in this issue. One of the cool takeaways is that accounts can have arbitrarily large storage trees, and we can load that into memory. And then we have another funny stuff, which is we might require nodes to have 512 gigabytes of RAM, which is completely nuts. But basically, the issue was closed when they realized that this cannot be done. Like, it's another bottleneck. And the conclusion was, we should move to a stateless clients or sharding, basically. So you can do parallel execution in Ethereum. So stateless is the way. I don't dig into many of the available solutions to solve the state bloat on Ethereum, just the state minimized design. But right now, I stick with account model is somehow bad. Then it comes UTXO as a blessing. This is Hal Finney inventing UTXOs and helping us to solve these issues. And basically, UTXO is an approach where you don't need a root state, so you don't have centralized state, so you don't have race condition, and so on. UTXO look like this, and they stand for unspent transaction outputs. So basically, this is how Bitcoin works, and it's like you don't have a big spreadsheet of balances from each user, but each user has some amount of money locked in some kind of program, and then you have like a bunch of programs with money that is not spent yet. So it's like a piggy bank. Basically, you put money into a piggy bank, and then you have your account with a bunch of piggy banks with different amounts of money inside them. And when you want to spend some of this money, you just destroy as much as piggy banks you need to fulfill the desired amount. Then you create a new piggy bank with that amount of money and send that to the recipient. Another analogy might be cash. So basically, when you pay with a $100 bill, let's say you are willing to pay 30, so you have 17 change. Well, the cashier might be burning that $100 bills and creating 2 new bills from scratch. A $30 bill for themselves and a $70 bills for you. So it might look something like this. A bunch of UTXOs are going to be merged into one transaction to create a new UTXO. A more accurate depiction might be this one, where you have 50 Bitcoins, you send them into a transaction and split them 0.5 into another recipient and 49.5 for yourself. Another account might be the same, so it's going to merge a couple of UTXOs in order to create a couple of new UTXOs. So it's like an ongoing process forever. So why is this parallel? Well, because you remember race condition, where you are trying to access the same slot in memory, where you don't have that problem because of atomic state. Basically, you are having pieces of storage, pieces of data flying around in the blockchain, so beforehand, you know they are not colliding together, which is amazing. UTXO killing the root state. Wait a second, I'm Sandusky. I'm developer relations engineer at Fuel Labs. You can find me like this on Twitter. We are building the rollup OS for Ethereum, so it's pretty cool. Go to fuel.network to check it out, please. Skip the selling. We were talking about UTXO, so good, right? But this has a history behind, and it's a pretty cypherpunk history. This concept kind of was invented by Hal Finney back in 2004, and basically comes as this concept, reusable proof of work. This is a screenshot from the archival website, which is started at the Nakamoto Institute website. And they even have the slides, so I'm going to reuse some of the slides. This is based on top of Hashcash. Hashcash was built in '97 by Adam Back, and basically is proof of work. They invented a way to tokenize expensive computation in order to avoid email spam. The issue with this is like you cannot exchange them, and Hal Finney had this theory that if you're receiving a lot of Hashcash, proof of work means that you're a real human being. Spammers often don't receive emails, therefore they don't have proof of work related to their own account. So they say, if you already have computation proving that you are a real human being, you should be able to spend that tokenized computation in order to perform other actions. And this is basically the UTXO model. You have proof of work tokens. You have a data structure that allows you to spend that tokenizing computing. And then you have a network of decentralized protocol and servers willing to verify that information. This is basically Bitcoin, almost 5 years before of the white paper. So thank you so much, Halfini, for building this technology that makes us so happy. Now we go into a state minimized design, where basically we are trading off bandwidth with the state. In Ethereum, we have different kind of storage information. We have like cold data and memory, which is like ephemeral information. Memory is like the scope variables you are using within a function, and cold data is read-only information that comes as form of parameters within the transaction. And then you have a storage, which is permanent information. Storage might be like going to a restaurant. So you are like walking so lightweight, you go there, they have the food, you eat, you leave. And then you have cold data, which is like keeping your own lunchbox wherever you go. So basically, for a storage-based execution, you have all the information in the contract, and then you send lightweight transactions to avoid taking so much bandwidth. And then you have cold data, where actually you are sending big transactions to pretty stateless contracts. That's why it's called state minimized. Uniswap B3 is doing this, actually. This is like the staker, a section of the staker contract. And basically, you see that they are just storing a derivation of some data structure. And each time someone is willing to get information from that incentive, they are basically computing back again the information. And it seems counterintuitive because we learned that we want to avoid computing things many times. So we build caching and all of this other stuff. But actually, for blockchain, this makes sense. And it's called state hydration. So basically, you are keeping track of small pieces of data in the blockchain and then using computer power to reiterate that data and have meaningful value. And then is where predicates come into action. Basically, this is a stateless account abstraction. It's a new kind of primitive built on the Fuel network, and it's something really cool that I would like you to see. So we began talking about UTXO, and we end up talking about predicates, but in the middle, there's pay-to-script hash. This is something coming from, I think it's BIP 16 by Gavin Anderson. So what the fuck is pay-to-script hash? Well, you know the standard kind of account in Bitcoin and everywhere else, which is private key, elliptic curve, and then a public key. So you deposit money or associate money to that account, and then a private key is able to like spend those resources. Where in the case of pay-to-script hash, you have like signatures, and you have a redeem script, which is some kind of puzzle designed to define the conditions whether UTXO can be spent or no. So basically, you are having a public key that doesn't come from a private key, but from a script. So that's like the idea. You can imagine that as like the lockboxes you use for Airbnbs. So it's not a person giving you the asset, but a device in the world having some kind of puzzle, and then having some kind of asset that you can unlock. So if you know how to solve the puzzle, you know how to get the assets. That's the whole idea. But what's the issue with pay-to-script hash? Why is it not like so widespread use? Well, basically because Bitcoin is dumb. Like you can do almost anything with Bitcoin so far. That's why we went into Ethereum. Ethereum decided to go with the account model rather than UTXO model. So that's where predicates become so useful, because predicates, so powerful, so good, so gentle, are some kind of mix between the UTXO standard approach, powerful VM such as the Fuel VM, high-level expressive and useful language such as Swaylang, which is a DSL build based on Rust, and the philosophy behind pay-to-script hash. That's where you get predicates. A predicate is just a pure function that you hash and get a public address. So it's like the source code is the private key. And this is basically a stateless account abstraction. Why? Because you are not storing this code in the chain. You are just keeping track of the hashes. And whatever who has the input script is able to spend the money that is there. But not with the code only. You have to fulfill the conditions of the code. So a predicate might be basically a functor. This is for the computer nerds. So predicates are like wallets. They can receive assets, they can hold assets, and they can spend assets. Predicates are like wallets. So they can be deployed, and they cannot be deleted. So they are pure functions with a Boolean return, and if the result of the predicate execution, we call it evaluation, if the result of the predicate evaluation is true, well, you can unlock the assets within that predicate. A slide about reusing proof of work, I'm reusing the slide. Spending predicates. So basically, you need the predicate code, as I told you. You need a transaction that fulfills the condition of the predicate. You need the full client and the full UTXO set. This is basically like the blockchain. And then you have a new UTXO. So it's basically it. It's like UTXO, sending a transaction between them, but adding an additional step, which is solving a puzzle. So you don't have to keep the money yourself. You can keep the money in a stateless abstracted account, and you can spend that by fulfilling the conditions of the predicate. Differences between contracts and predicates. Predicates won't access on-chain data. Why? Because they are pure functions. They can read data from smart contracts. They are not aware of time, and they can read hash numbers or block numbers. But they can read input and output coins of the transaction. They have access to transaction script and transaction bytecode. This chart is coming from our own guide on predicates, which is Predicates 101, Building Stateless DeFi Applications. You can check it out just right here, but I'm getting the QR again. Bonus track, all VMs and UTXO. This is another project right now leveraging on the UTXO approach. We have Aztec, privacy solutions. We have Nervos, which is like an intent-based network. We have Findora, which is some kind of Ethereum sidechain. We have Alephium, and only one of them has powerful predicates, which is Fuel Network. So, summary and a few conclusions. State bloat is bad for decentralization. Account model can be parallel. UTXO is so good. Halfini, thank you so much. And predicates are so amazing. So if you want to start building stateless DeFi applications, you want to mess around with predicates, you want to build these crazy off-chain, on-chain secure functors, well, come and join this QR code. I promise that it's not a security threat for you. I just need a tracker for the event so I can show it to my manager. But yeah, that's it. Thank you so much. Do we have time for questions?
We have time for one or two short questions. Are there any questions?
Is there anyone? However, we can meet outside and keep talking about computer science stuff. However, thank you so much for attending, and hope you have a great time building with predicates. Thanks.
Thank you.